Hello, hello, hello. Hello, hello, hello.
Yeah, it's coming. Check that mic. No, not that one. Next one. Yeah, that will come.
Hello. Hello.
Check, check.
Hello, hello.
on Zoom as well as group. Yes, yes. Yeah, please. Hi everyone, warm welcome to this seminar. So we apologize for running a bit late. So we will be starting in about 10 minutes. So yeah, sorry for the inconvenience.
today. This is the CAMOST, which is the Center for Atomic, Molecular, and Optical Sciences and Technologies. Yeah. Can somebody confirm who is online on Zoom? If I'm audible, can you see the screen? Can someone confirm?
Yeah, audible.
And is the screen visible?
Yes.
Oh, good. Rajesh is there. Good. Nice seeing you, Rajesh. So very hearty welcome to all of you, those who are here in person, and of course, also those who have joined in a video conference. So CAMOST, which comes from it stands for the Center for Atomic, Molecular, and Optical Sciences and Technologies. This is a joint initiative of the two institutions, IIT Tirupati and the IISER Tirupati. And these two institutions have collaborated with each other in a number of activities. Atomic, molecular, and optical sciences is one of the areas, but there are also other areas in which the two institutions have worked together. We jointly hosted a conference whose proceedings also were published by Springer. And since then, a number of joint initiatives were taken by the two institutions. The first director, Professor Ganesh of IISER, and Professor Satyanarayana, director of IIT Tirupati, gave us a lot of support and guidance, which enabled setting up the center. We are very privileged that we continue to have this support from Professor Shantanu Bhattacharya, who is also with us today. So very hearty welcome to you, sir. Very hearty welcome, of course, to Professor Satyanarayana, who has always been a big force behind CAMOST activities. And we are very privileged to have a very distinguished speaker today, Professor Arun Pati. So very hearty welcome to you. So will request Sunil to offer a bouquet of flowers to Professor Pati. Sunil. Aniket, may I request you to offer a bouquet of flowers to Professor Bhattacharya? And Sambuddha, please offer a bouquet of flowers on our behalf to Professor Satyanarayana. So we have been able to organize a series of seminars. This is an expanded consortium because it is not just the IIT Tirupati and the IISER Tirupati which have come together, but we are also very closely working with S20, which is the science division of G20. And it is represented by the Indian National Science Academy, and they have also participated in organizing this program. So without taking much time, I will like to invite my colleague, Dr. Vinay, to present a short report on CAMOST. It is particularly significant because we just completed 3 years. So CAMOST was set up on 14th August 2020. So it is just 2 days that we completed 3 years. And Vinay will present a short report to you. Vinay?
Um, so hearty welcome to all of you. So it's my privilege to present the annual report, or actually the report of all the last 3 years of since the inception of CAMOST. As Professor Deshmukh has mentioned, this center has come into being with inputs from from IIT Director Professor Satyanarayana, then the first Director of ICER, Professor K. Ganesh, and also very valuable inputs from eminent scientists, Professor C.P. Safwan from IUIC Delhi, Professor Dilip Angom from TRL Ahmedabad, Professor E. Krishna Kumar from TIFR Mumbai, and also inputs from several other CAMOST Scientific Advisory Council members. And we continue to get support from the new director, Professor Shantanu Bhattacharya, who is the director of IIIT Tirupati. And this particular program, which is it's jointly organized between CAMOST and the G20-S20, we also received very valuable inputs from Professor Ashutosh Sharma, President INSA, and also Professor Narendra Mehra INSA. So before presenting the report, I would also like to thank all the students, staff, and faculty members of ICER and IIT Tirupati and ICER Tirupati. We have about almost 10 colleagues each from ICER and IIT who are contributing to the growth of this center. So the first inauguration session was done on the eve of the Independence Day. It was on 14th August 2020, when Dr. Arvind Mitra, Scientific Secretary, Office of Principal Scientific Advisor, Government of India, was there to inaugurate this center. And we had distinguished lectures from eminent scientists, Dr. Aditi Sende, Dr. Lokesh Trivedi, and Dr. G. Rabindra Kumar. The center is set up with the following vision. So I will not read the whole thing, but in short, it is to attack frontier problems in atomic, molecular, and optical sciences and technology, and twofold: to solve frontier problems and also nurture future scientists. We want to create human resources who would be able to solve tough problems in AMO sciences. And also in particular, we have a special emphasis these days on quantum technologies, where AMO sciences and technology can contribute. So we have the following thrust areas.
Excuse me. Hello. Hello. The sound is very low. Can you please come closer to the mic?
Okay, sure. Is it audible here?
No, still not.
Okay. Now?
Yeah.
Okay.
Better.
I really have to keep it close.
Thanks. Yeah.
Okay. So we have the following thrust areas based on the expertise that we have among the faculty at ICER and IIT Tirupati. Ultra-fast physics, quantum dynamics on attosecond timescales, quantum computing, quantum communication, and quantum sensing, quantum photonics, which includes cold plasma applications, laboratory astrophysics, astrochemistry, and atmospheric sciences, optical tweezers for biomedical applications, single molecule magnetism for high density data storage, quantum chemistry and statistical mechanics, and high technology devices. So these are the current thrust areas based on the various faculty who are part of CAMOST. And we are guided by eminent scientists from India as well as abroad. Just to read out a few, Professor Dilip Angom from PRL Ahmedabad, Professor Krishna Kumar and Professor Safwan, whom we are engaged with since the beginning of the institute. And also we have inputs from scientists abroad, to just to name a few, Professor Dmitry Budkar and Professor John Costello. So in the last couple of years, this is the report for 2020 to 2022. So we had a few seminar series and conferences. The first one was in Advances in Atomic, Molecular, and Optical Sciences 2020. This was during the COVID. So it was online, and we had about 37 talks spanning over 5 days by leading experts from many countries. And select talks were also published in a special issue in IOP journal Physica Scripta. We had a short online course on Introduction to Quantum Optics. This was in July 2021, where we had 10 lectures and a few tutorial sessions by Professor Sanjoy Majumdar. He's a professor at IIT Kharagpur, and we had a large number of participants, about 200 of them. And we had 6 webinars during this period and also about 50 publications in peer-reviewed national and international journals and about 2 book chapters. So to celebrate the first anniversary, we had a colloquium series where distinguished speakers and scientists from TIFR, Professor Ravindra Kumar, Professor Vijay Raghavan from TIFR, Professor Urvashi Sinha from RRI, Professor Dmitry Budkar from Germany, and Professor Peter Brugman from University of Minnesota gave distinguished lectures. And as part of the second anniversary, we had talks by Professor Roland Wester, Professor Arun from IIT Madras, and Professor Jan Michael Rost from Max Planck Institute, Dresden. And coming to this particular year, which is just concluding, we have about 30 publications in peer-reviewed journals and 1 book in quantum mechanics. This is authored by Professor Deshmukh. Will be soon released in about a couple of weeks, and it will be published by Cambridge University Press. And we have sponsored research grants, about 5 projects to the tune of 1.3 crores. And the most recent event is this particular CAMOST-G20-S20 Consortium seminar series on disruptive sciences and technologies. And we have as outreach partner, the Indian Association for Physics Teachers. And we hope to grow over the next year and contribute more to the AMO sciences and technologies in the country and abroad. Thank you.
Thank you. Thank you very much, Vinay. May I request Professor Satyanarayana to please speak a few words, address the gathering.
Good afternoon, everyone. Thank you, Professor Deshmukh. When CAMOST was initiated a few years back, this was an outcome of a number of series of workshops, conferences that Professor Deshmukh and our colleagues from both IISER and IIT had been conducting. They were bringing in a number of distinguished scientists in this area, whether it's both from abroad and from India, TIFR, and various other IITs and IISERs and so on. So the feedback that was given to us was, between the 2 institutes, you have 7, 8 young people working in this broad area of atomic, molecular, and optical sciences. And with the guidance and the leadership that Professor Deshmukh was providing, it's a good opportunity to, to work together and take this area forward. So that's based on that. The proposal for the center was formulated with the lead taken by Mr. Deshmukh, along with other colleagues, Arijit, Ritesh, Sunil from IISER, and other colleagues from both the institutions. And immediately, Professor Deshmukh and I were very excited about this opportunity that we have at the 2 upcoming brand new institutions, and also provided an opportunity to work closer. From the beginning, both the institutes have so much in common. We had a common foundation stone program in the IISER site there for 3 institutions, including IIIT H3 Then our academic programs were launched the same week in the first week of August 2015. And the campuses are also closely located. So we thought from the beginning, we should set a model of institutions working together. And so this provided a great opportunity for us to create a platform where people come and start talking and start working together. And in fact, we have enabled that the framework that students can go take courses across both the campuses. So the students have a larger basket because both have, of course, IISERs are basically science institutes. IITs are both technology, engineering, and science, with also humanities institute. So we give the students also a broad large basket of courses from which they can choose, and the credits can be transferred across the campus. Of course, this involves a little bit of tweaking with your timetables and so on, so that you can accommodate the timetables. But if you really want to do things, you'll find a way to get it done. Okay, it's the willingness to do things. Any number of reasons why it's difficult. For example, the credits were a little different, the grading systems were a little different between two institutes, but you can really put your heads together, you can map it and make it happen. And more importantly, we also saw this opportunity of the quantum mission that was getting formulated at the national level. In fact, earlier, the name of Professor Ashutosh Sharma was mentioned, current chairman or president of INSA, president, right? President of INSA, former secretary DST, during whose time this proposal was being formulated. And if you really want to be active or a serious player in this mission, we also have to show some activity coming out of these institutions. And this gave, and having such a initiative gave us an opportunity also for people to work together and show that we have an active group working here. So that was one of the other, at least from my perspective, a big motivation to bring this group together and make them work together, so that we bring in some credibility and some, visibility in terms of being a player in this quantum mission of the country. And finally, after last 2 years, it was any day the mission was going to be launched, and finally it got launched recently. And so this year I can see most of the talks are very much aligned towards the quantum area. A few talks, of course, from the other topics also. And we are very happy to see that one of the leaders in this particular area, Dr. Arun Pati, has been brought in as the lead speaker, and also positioning it under the banner of the G20-S20. Once again, India has taken the leadership of G20. A number of events are being conducted under various heads, one of them on science, the others on education, and so on. And positioning the series of talks under this banner also, I think, is a very good move on part of the organizers. And also, working with a few organizations, for example, INSA. I spoke to Professor Ashutosh Sharma, and Professor Deshmukh has been in touch with INSA to also support this, and they're ready to support these various activities under the S20 initiative. So now we have finished 3 years, completed 3 years of CAMOST activities. We need to take it to a different scale, and nothing can happen without funding. So we need to find ways of creating a good corpus, endowment, funding source to bring in many more eminent scientists to come closely with our group. So other day I was discussing with Professor Deshmukh how we could probably do it. In addition to writing joint research projects. And most importantly, what I also really liked is the eminent scientific advisory board. In addition, faculty from a number of other institutions that are associated with CAMOST, including IIT Madras, and I've seen IIT Mandi and a few other institutions. So they're also associated with CAMOST activities. So it's not just restricted to these two institutions. So we're trying to make it a much more broad-based initiative. So towards that, I think the next 1 year, we should ensure that we bring in reasonably good amount of funding to scale up the activities to a different level. And so that, I think, let's work towards that along with Professor Santanu Bhattacharya and the team. Let's see how to make that happen. So you have the series of talks going on till October, middle of October, very eminent talks. So looking forward to a very successful event. And Professor Ashutosh Sharma said he would like to come to Tirupati to visit both our institutes. So let's see if we can fit him into also the program so that He said till August he's busy, August, September, but I think October he can make it. I can see there's a panel discussion that is being planned and so on. So if we can get him to do that, that'll be good. So thank you very much. All the best. Yeah.
Thank you very much, Professor Satyanarayana. As I mentioned, he has been guiding us from the very beginning, and we are here partly because of that. So thank you very much. May I invite Professor Bhattacharya to speak to us? So Professor Bhattacharya has recently taken charge of IISER Tirupati, and this is our first opportunity to listen to you, sir. Thank you very much.
Thank you very much for the opportunity given to me for being present here. I think I'm very pleased to note that the Indian Association of Physics Teachers, IIPT, has started doing this collaboration with IIT Tirupati and IISA Tirupati and also Indian National Science Academy. And they have initiated this CAMOST-G20-S20 Consortium seminar series. This series is woven around quantum-based topics relating to the emergence of phenomena such as quantum information, quantum computing, quantum technologies, so on and so forth. You know, I had my prior association at the Indian Institute of Science, where one of my colleagues, led Dr. Basant Natarajan, he actually brought probably the first footprint of using quantum-based technology in this country. I remember a young man, he started building his quantum optics lab right from MIT. And that is something one needs to emulate. And those days, nothing was available. And he was going into the downtown Bangalore to get some of the parts and assemble them. And that's from scratch. And I was also associated with another very old institution earlier, that is Indian Association for the Cultivation of Science, where Sir C.V. Raman fetched the first and only Nobel Prize till date in science from this country. And there were many discourses where the explanation for Raman effect using quantum mechanics were discussed. And in fact, I had an opportunity some years ago when the then Chancellor of Germany, Angela Merkel, her husband was actually a quantum physicist. And they were very much interested in the quantum phenomena involving Raman effect. So this is, you know, I am sure I don't need to explain here. These AMO, atomic, molecular, and optical sciences is an area which is going to be very, very important. And I'm sure the organizers will make every effort to disseminate timely information to a strong network of its members. I'm particularly elated to note that Professor Satyanarayana has spearheaded this program along with my predecessor, Professor Ganesh. And I think this is the hand-holding that we do between IISER and IIT at Tirupati. Will continue in many other programs. But this CAMOST program that you have created here will serve as a role model. As physics subject society, IIPT members should get a timely exposure to such significant advances in the state-of-the-art knowledge, which is crucial to the success of our national mission on quantum technologies, which is announced by Government of India. And I would imagine that this forum will actually catalyze creation of various kinds of proposals through which you can secure funding under this mission. I'm particularly happy to note that Professor P.C. Deshmukh, an honorable member of the fraternity of IIPT, is spearheading this imaginative series with much sincerity and seriousness. Young students, many students who study physics at colleges and universities, I find that they struggle with maths, particularly when they have to explain quantum mechanics, matrix mechanics, spearheaded by Heisenberg and Schrödinger. I think we need to look at pedagogy and teaching very significantly. We have heard of quantum mechanics, quantum chemistry. What about quantum biology? I think you mentioned some of these things like biomedical technology, which will be spearheaded. And quantum biology, which is concerned with influence of non-trivial quantum phenomena, which may be explained by reducing biological phenomena to understand various kinds of fundamental physics related issues, although these effects are difficult to fathom at this point of time. But nevertheless, future lies there, in addition to some of the technologies that one can imagine. So again, I would reiterate that I hope your activities will lead to submission of various kinds of joint proposals among the stakeholders of the field to develop a new signature in quantum science and technologies in India. I'm sure this will augur well in terms of the widespread dissemination of the most compelling advances of quantum topics as we speak. And I wish every success in this endeavor. Thank you very much.
Thank you very much, Professor Bhattacharya. I'm reminded of the workshop I attended more than 40 years ago at Uppsala. And Professor Piralov Lodin was the director of that workshop. And he said that the 20th century was revolutionized by quantum theory and the theory of relativity. And the 21st century, it would be by quantum biology. So what you said is very timely. We are already more than 2 decades into it. So I think it's going to be very exciting to see what happens in quantum life sciences in the coming years. Thank you very much, sir. Let us move on to the to Professor Pati's talk this afternoon. Anybody who is reading about quantum information sciences does not need an introduction to Professor Pati. For more than 20 years, he has made extremely important contributions. I think your first paper in Nature was more than 2 decades ago, I think. But for the benefit of some young students over here, I request Dr. Sambuddha Sanyal from IISER to introduce Professor Pati. Sambuddha.
Thank you, Professor Deshmukh, and thanks to both the director and all the audience for being here. So, as Professor Deshmukh said, that Professor Pati doesn't really require an introduction. On the other end, if one chooses to introduce him, it can become very long. So I'll try to strike a balance between these two extremes. So Professor Pati has a 3-decade-long career at the front line of quantum information, quantum computation, and the fundamentals of quantum physics. And it's very appropriate that today he is opening this consortium. And he have done his PhD from University of Bombay at 1989. Then he was a scientist at BARC. Followed by that, he took up a position as a EPSRC fellow at University of Wales. And then he had almost a decade at IOP as a visiting scientist. And then he was a professor at HRI. And very recently, he is the head of the Center of Quantum Science and Technology at Indian Institute of Information Technology at Hyderabad. And he is also the director of Quantum Ecosystem and Technology Council of India. And Professor Pati have received many honors, just to name a few. He was the young physicist, received the Young Physicist Award both from Indian Physics Association and Indian Physical Society. And he got the Samanta Chandrasekhar Award from Government of Odisha, and he is elected Fellow of Indian Academy of Science and National Academy of Science. And he also received the J.C. Bose Fellowship. So again, to talk about his work can become itself a talk. So I'll just briefly overview some of the fundamental, most important contributions of him among many. So he proved some of the cornerstone no-go theorems in quantum mechanics, such as no delete theorem and no hiding theorem, which are which are like as important as is no cloning theorem, and makes the fundamental building block of quantum teleportation, thermalization, and even black hole information paradox. Spans over many wide range of problems which are not immediately obvious earlier. And he have came up with remote state preparation protocol, which is another cornerstone idea in quantum communication. And he introduced the concept of geometric phase for mixed state, which was experimentally discovered later. And he proved several stronger uncertainty relations than Heisenberg uncertainty relations, to name a few of his many contributions. So with this brief introduction, I will just, because as I said, it can get very long, so I will just like to hand over this stage to Professor Pati for his talk. Thank you.
Hello. Is it audible? Okay, so let me start by thanking Prof. Desmukh for inviting me to this G20-S20 Consortium seminar series. And I see that this CAMOST is doing a great job in trying to motivate young scientists and young generations in the field of atomic, molecular, and optical physics, which is the basic building block of future quantum technology. So and also I thank IIT Tirupati Director Professor Arun and also Professor Bhattacharya for their continuous support to this event. So today I'm going to tell about some of the basic things that one should know about quantum information. These are like setting the rules of quantum, quantum computing, quantum communication, or future quantum devices. When you build some device, what are the rules you should respect, whether you should do this or should not do this, So these are the things that I will try to highlight during this talk. And I will try to be a bit general, and once in a while, maybe I will display some of the equations, but don't worry about mathematical equations. I will try to be as, general as possible, okay? So, okay. So before going to tell about the how different is quantum information from classical information, let us try to look back. What do you know about classical information? So in classical information, we know that you can store your classical bit using two distinct states like 0 or 1, and that you can do by choosing any two distinct physical states of a classical system. Okay, so and you can encode one bit in this two logical state, and then you can do various tasks using classical laws of physics, and that's what you do all the time, whether you talk about computer or your desktop or laptop or mobile. All the time you deal with classical information. But what happens is you never find a classical bit in combination of 0 and 1. Okay, at any given time your classical bit will be only in 0 or 1. But when you go to quantum world, we know that a quantum object can remain not only in distinct physical state, but also it can remain in combination of these distinct state. Why this is so? That happens essentially due to your linear superposition principle. And this is the key concept that you see when you go from classical world to quantum world. Okay. And that allows you to new way of storing information in quantum states. And this simple realization has so much remarkable consequence that we see today. The whole quantum computing, this field is essentially emerged from this simple notion. And this is the thing that was realized by David Doyce in 1985, who tried to propose the notion of quantum computer, using this superposition principle. And quantum information, in a larger sense, is trying to exploit these basic principles of quantum mechanics for various information processing tasks, which are otherwise impossible. Okay, so this is the bigger goal. So what you want to do is, using quantum mechanical principles like superposition and few more things that I will try to highlight, what more you can do, what new things you can do, what amazing things you can do when you build these quantum devices. That is the bigger goal. Okay. So quantum theory, when you think of, essentially the whole hello, yeah. So the whole structure of quantum theory is based. Hello, yeah. So the quantum theory is based on two key concepts. That is, one is called linearity and second is unitarity. What this means? It means that whenever you have a quantum system, you know how system changes in time. This is essentially your familiar Schrodinger equation. Okay, the Schrodinger equation that you know in your MSc level is essentially a dynamical equation which is linear and it obeys the unitarity. Okay, and these two things are so fundamental, so unique to quantum mechanics, that any deviation from these two basic tenets, till now nobody has found it. Okay, so this is really remarkable. And what I'm going to talk today is essentially based on these two key concepts. Okay. Not moving next. This is also some issue with the battery, or no, this is not working, this one. Okay, now it's okay. Yeah, so let me tell you about a little bit about quantum bit. So what is essentially quantum bit? When you think of a quantum system, like say electron or photon or atom, anything you can think of. So suppose it is an electron, okay, spin of particle. So you say that if it is up, then it is 0, and if it is down, say it is 1. So these two distinct states can encode a single classical bit. Okay, but then as I said, by the linear superposition principle, we know that we can have a state which is alpha up plus beta down, and that state, if you translate to this logical language, you have essentially alpha 0 plus beta 1. So any state which is of this type is also an allowed state in quantum mechanics, and that is essentially the notion of quantum bit that emerges, from this superposition principle. So any arbitrary state of a two-state quantum system is actually a quantum bit. So what you see, the first difference is that a classical bit can remain in either 0 or 1, but a quantum bit like Q bit can remain both in 0 and 1. Okay, and this inherent parallelism is responsible for new type of computation. As I said, the notion of quantum computation, which is not there in classical world. And this was realized by David Doyce in 1985. And over the last 5 to 7 years, there is a global race in trying to build quantum computer. So people are trying to use superconducting system and ion trap and optical devices and different other physical systems to build quantum computers. And there are a lot of interest, a lot of excitement, a lot of funding coming from governments, coming from private industry, from angel investors and so on. So this is really huge impact has been created over the last 5 to 7 years. So before I proceed to tell about the basic differences between quantum information and classical information, let me try to tell you some simple notions about this quantum bit. So I just said, if you have a physical quantum system like alpha 0 plus beta 1, we know that to describe the state of the single quantum bit or qubit, we need two complex number, alpha and beta. Okay. And when I say that the state is unknown, essentially, if the complex number like alpha and beta are not known to me or known to you, then you will say that this quantum bit is unknown to you. Okay. And if you know the alpha and beta, then the state is completely known to you. So how does that work? Essentially, it means that if I prepare a quantum state like a qubit myself using some physical device, okay, I know what is alpha and what is beta. Okay. So to give a simple example, consider a single spin initially in say off state, and you switch on your magnetic field, it will undergo some rotation because you know yourself how much field, how much the strength, how much with what angle, what theta and phi you have applied the field. You know how the state will rotate. So you know the theta and or you know what is alpha and beta. In that case, you know the quantum state. But if I have prepared the state and I give it to you, the state is completely unknown to you. Okay. And as you know from quantum mechanics, basic quantum mechanics, you know that to determine the state of a quantum system, you need identically prepared, infinite number of identically prepared quantum systems. Then only you can determine the quantum state. But given a single quantum state, it is completely impossible to determine what is alpha and what is beta. Okay. So this is the key region that you will see that leads to so many no-go theorems in quantum information. So given, as I said, given a single quantum, like single qubit, in this kind of unknown state, it is impossible to determine the state. So if you ask the question, how many bits do you need to specify a qubit? You need infinite number of bits. Because to specify the real number, you don't know where it is. If you imagine the block sphere to represent the quantum state, it could be here, could be here, could be here, anywhere, in the block sphere. So you don't know what it is. So you need infinite amount of information. But when you do a measurement on a quantum state like on quantum bit like this, you will get only 0 or 1. So essentially, you will get only one classical bit. So even though it is essentially vast amount of information, but by doing measurement, you can extract only one classical bit. So that is the the drastic difference between a classical system and a quantum system. So even though it has a large amount of information, we can extract only one bit by measurement. So most of the information is essentially inaccessible for an external observer. You don't know what is there inside. Okay. So there is another notion called quantum entanglement, which is often used in quantum information, quantum computing, and this was already introduced by Schrödinger in 1935. And at that time, he realized that this is something which completely, departs from classical line of thought. So, you can see the power of Schrödinger's thought at the time, so he could really appreciate, really emphasize the importance of this quantum entanglement at that time. So the quantum information, as I said, is a vast field, and under this banner, you have several subtopics like quantum computing, quantum communication, quantum cryptography, and many other things. So under this, you have quantum algorithm, quantum computational complexity, try to study decoherence, error correction, you try to do experimental implementation, and so on. In quantum communication, there are several things. I have just highlighted a few things, that is teleportation, dense coding, remote state preparation, remote control, and many more things. Similarly, here you have BB84 scheme, you have entanglement, state-based scheme, secret sharing, and many more things. So in all these sub fields, what is the thing that really drives this field? Essentially, you will see that in all these, quantum coherence or entanglement, quantum correlation, and non-locality, these kind of non-classical features essentially play some role, in trying to achieve all this. So quantum information has been there, this field already, is there for last 30 to 40 years. And I've been working in this field almost for more than 32 years now. So still, there are many things still we don't understand. For example, here is a quote from Richard Josa, the person who discovered the first quantum algorithm, Richard Josa algorithm. So he's the same person here. So he says that quantum information theory has developed into a vigorous field of research. Indeed, the very idea of viewing quantum state as carrier of some kind of information, albeit unknowable in classical terms, leads to naturally interesting questions that might otherwise never have been asked and corresponding new insights. So essentially what we're trying to tell is that even though the field has developed so much, it has progressed so much, but if you start asking the question, how different is quantum information from classical information, that will lead to new insights and new, implications, new applications, which can have wide impact on different sub-disciplines of quantum information. Like it can have an impact on quantum computing or quantum communication, or quantum cryptography, many more things. Okay. So coming back to the notion of quantum bit and how different it is from classical bit. First thing to realize is this quantum state psi, which describes your physical system, carries both classical and quantum information. And as I said, it has potentially vast amount of information, which is inaccessible. And possibly that inaccessible information is something to do with quantum information. And the amount of information that you can extract from a quantum state by doing measurement is essentially your classical information. And to understand these fundamental differences, will tell you many new things. So therefore, it is important to know what are those differences between classical and quantum information. And moreover, these differences will tell you how quantum, or what is so quantum about this quantum information. Okay, that is the kind of motivation with which I started to explore, this few of the no-go theorems. So these differences also has, or they have fundamental and practical applications. Fundamental because they can shed new light in the boundary between the classical and quantum information, and it can have practical application because you can exploit these for various security purposes in quantum computer or even quantum communication channel. If some of you are familiar with quantum cryptography protocol, the famous no-cloning theorem that was discovered in 1992 is something that plays a major role in trying to give security to quantum cryptography protocol. So that really plays a major role. Okay, without no-cloning theorem, you will never be able to prove the security of the cryptography protocol. Okay, so what are the no-go theorems that I'm trying to highlight here? So first is the cloning of quantum information, which is essentially a no-cloning theorem. I will try to just highlight. Then there is something called deleting of quantum information, and there is something called design of NOT gate for unknown quantum bit, and partial erasure, hiding of quantum information, and then masking of quantum information. So all these operations which are possible in classical world, they are not possible in quantum world. Okay, that is why we say that these kind of operations are not allowed in quantum information. That then you say, okay, these are your no-go theorems. Okay. So here is your no-cloning that already you are familiar. Essentially, what you want to do is you want to build a device essentially like a Xerox machine, and you have one input, one blank state, and at the end you want to get to copy. Okay. This is exactly what you do in your Xerox machine. You have the machine, you have the information that you want to make copy, you have a blank state, blank paper, you switch on the device and get original along with the copy. Okay, exactly same thing you want to do here. Okay, and we know that you can do this for classical bit, because if classical bit, if you have 0 and this is your blank, then you can take to 0 0. If it is input is 1 and this is blank, you can do it to 1 1. And this is exactly possible using your classical XOR gate. Okay. But what happens in quantum mechanics? In quantum mechanics, if you know the state, you can clone it perfectly. Also, if you are dealing with quantum bit in orthogonal state like 0 and 1, you can also do same thing, because orthogonal state, as I said, they encode classical information. So if you are given 0, 0, and you can take it to 0, 0, it is 1, 0, you can do it to 1, 1. That is perfectly allowed. Okay. But what about this scenario? So turns out that you can never be able to satisfy this. That is, this is not allowed in quantum mechanics. So the statement is there is no linear transformation that can take this to this kind of, okay. So if you want, you can include the state of the machine itself, but if you don't want, you can discard it. So essentially you want psi 0, should go to psi. And this was not allowed, essentially. It was proved by Jurek and, Utters and Jurek in 1982, okay. Few years later, in 1986, similar thing was proved by Nguyen in 1986, that had to do with cloning of non-orthogonal state. That is, he asked the question that, is it possible that you are given psi 1 and psi 2, which are not orthogonal, and you want to create this psi 1, and psi 2, psi 2. And this is just one line proof. If you are familiar with linear algebra in your graduate level, you know that if you have to design a transformation set and you want to respect unitarity, you know that if you multiply this set, that should be equal to this set. And that essentially means that you should satisfy this. But this will never be possible because these are non-orthogonal. If it is orthogonal, this is 0, it is okay. But if it is not orthogonal, if it is less than 1, you will never be able to satisfy this condition. Okay. So that is essentially the one line proof that you can never be able to make copy of non-orthogonal state. The proof is simple, but it has profound implication, in quantum information. So quite late in 2004, Richard Josa, he tried to prove a stronger version of no cloning. So what he asked is the following question. He said, okay, classical information, I can always make copy. And that's what you do all the time. You copy your file from mobile to laptop to desktop and so on. Okay. So classically, everything is fine. You can do whatever you want to do, but quantum mechanically, you are not allowed to do. So is it true that there is something missing in quantum case? There is something you are lacking or something you don't have. That is why you are not able to make copy. Okay. So he asked the following question: what extra information you need to supplement to the input copy so that you can produce 2 copy? Okay. In classical case, you don't need anything extra. Whatever is given to you, you can make 2 copy. Okay. So it turns out that in quantum case, you have to recreate the information from scratch. Okay. The input is not playing any role in making copy of the original. Okay. So unlike the classical case, quantum case is drastically different in this scenario. Okay. So this is the theorem. Again, don't worry about the mathematical statement. Essentially telling you that this kind of transformation is possible if and only if this input, this blank, is already been able to transform to the original. That means you have to recreate the state from scratch. Okay. The input is not doing anything. Okay. So that is the essential content of the theorem. So pictorially, you can see that like this. So this is possible if and only if you can make this to this from the scratch. Okay. That is the idea. So the proof is again, all you need is linear algebra. So it is again very simple. But if you want, I can go through, but if you don't want, I can skip this. Do you want me to go through this? So the proof is actually trying to do the following. So this kind of physical operation is possible if and only if this is possible. Okay. So what is the physical operation in quantum mechanics? Any physical operation in quantum mechanics is essentially unitary, whether it is closed or open. If it is closed, of course, it is unitary, but it is an open system. It is strictly not unitary, but you can always imagine that open system dynamics by bringing some additional quantum system and then evolving everything in a unitary fashion and a larger Hilbert space. Okay. So for the time being, forget about open dynamics. Everything is unitary. Okay. So if that is so, then the theorem is actually very simple. So if there is a physical operation taking this to this, of course, we have this, very trivial, okay? The second part, the converse is the following. Assume that this is possible. And as I said, by including a stress system, you can imagine this unitary evolution. And then if it is unitary, then if I multiply this side with different index, I get AI AJ equal to psi A psi J, okay, from this unitary condition. But then by simple linear algebra, I know that two sets of these vectors have equal matrices of linear product for all I j, if and only if they are unitarily connected or equivalent. That means I can recreate psi I from AI alone by unitarily from this. Okay, that means I should be able to build it from the scratch from AI itself. The input psi I not doing anything at all. Okay, in creating the copy. This is essentially the theorem. Okay, sorry. So you see the statement is actually very simple. First part is trivial. Second part just says that assume that this is possible, but by unitarity condition, you see that this you can recreate from AI itself. The input AI, which is sitting here, not doing anything else. You have to build it from AI itself. Okay, that is the idea. So this stronger cloning is telling you that you can never be able to create from the input. You have to build it from scratch. Okay. Okay, so let me go to the no deletion part. Again, I'm not going to prove it. Essentially, just I will try to tell the statement. But before I tell the no deletion theorem that we proved, let me try to tell what is erasure. Okay, in classical world, when you erase a bit, okay, essentially you take any input and reset to a fixed state. Like 0 can go to 0 and 1 can go to 0. And this kind of operation is never a reversible operation. Okay, this had to be irreversible operation. That means it will spend some amount of energy in doing the task, and that was essentially the realization by Rolf Landauer. And he proved that to erase a single bit, you have to generate entropy of k log 2. Okay. And this has implication in irreversible computation, resolution of Maxwell lemon, and so on. And that is also one thing that led to this insight that information is physical, because to store and process information, you need physical system. Okay. And what about a quantum bit? If you want to erase a quantum bit psi to 0, again, you cannot do by reversible operation. You have to bring some kind of irreversible operation. Okay. And why you cannot do by reversible operation? That is the proof is again very simple. That is, in quantum mechanics, we know that reversible operation is essentially unitary transformation. That means if you want to do psi to 0, you should see a contradiction. And what is that contradiction? Assume that you are given two states like psi and phi, and they are non-orthogonal. Okay. So, and then assume that there is unitary operation or reversible operation which can take psi to 0 and phi to 0. But then again, by same logic, the unitary evolution must preserve the inner product. Okay, that means I take this time this, I should get 0 times 0. So what this telling is unitarity implies that psi phi equal to 1. But I know that psi phi is a quantity which is less than 1. This can never be satisfied. This is a contradiction. Okay. And what about orthogonal state? Suppose I take psi to be 0 and phi to be 1. Again, you get a contradiction. Why? Because this side is 0 and this side is 1. 0 can never be equal to 1. Okay. So you see that there is no way that classical information nor quantum information you can erase by reversible operation. Okay. That means you have to bring some kind of irreversibility, some kind of energy cost to to achieve this task. And this is the reason behind whenever you want to delete some of your file in laptop, your laptop gets heated up. That is essentially happening because of the Landauer's erasure principle. Okay. So this shows in a simplest and profound way that neither classical nor quantum information you can erase by reversible operation. So let me come to deletion, no deletion theorem. Essentially, what you want to build is a device. You have two input, and you want to reset this to a fixed state keeping the intact. Okay. And I know that classically I can do it. I can classically take 0, 0 to 0, 0 and 1, 1 to 1, 0. But can I do this same thing but this quantum bit? Answer is no. And the proof is a bit involved, but you can show that it is impossible to delete one copy from the other one. Okay. So the more precise statement is there is no quantum mechanical transmission which can take this. Okay. And in proving this, you demand that the final state of the device should be independent of the input. Why you need this? Because you don't want to hide information in the, or don't want to keep the information in the machine itself. Okay. And you exclude the swapping as a proper deletion because you don't want information to be hidden anywhere in the deleting machine or any other part of the universe. And if you allow that, then by swapping and tracing, we know that you will be able to erase it, and that extra copy that you have here playing no role. Okay. So if you're able to really delete, at the end of the day, the information should not be somewhere in the device. Okay. So if you demand that condition, we will never be able to satisfy this. Okay. So you can do also similar proof for non-orthogonal state like set of states LSII. So given this kind of set of states II and its another copy II, is it possible to do this? Then you can prove that this is also not allowed. So the only option is that the information, if you want to forcibly delete it, you will find that the information which is missing from here simply be going and sitting some part of this ancilla state. And the second copy, you can always resurrect from the final state of the ancilla. So if you look at this no deletion and stronger no cloning, they have something common. And what is that? So in cloning, we see that the first copy gives no assistance in making second copy. And in deleting also, the first copy provides no assistance. So if you combine these two, you realize that to create a copy, you have to build it from scratch. That means you have to bring it from some part of the world where it already existed. And to delete it, you have to take it and keep it in some other part of the universe. Okay. So you can only import and export information, but you can never be able to create it or delete it. Okay. That is the message coming out from this no deletion and stronger no cloning theorem. And a few years later, this Rodegi group and Aditya Sen and Ujjwal Sen, who are at HRI now, they try to also show that this no cloning and no deleting, they are also connected to conservation of information. And they also try to connect this to second law of thermodynamics, which is quite powerful. There is another no-go result, which is essentially the design of dot gate. Okay. Classically, I know that I can design a NOT gate. I can flip it, 0 can go to 1 and 1 can go to 0. Okay. And this is a, this is part of the universal logic gate in classical computing. And if you want to do same thing for a quantum bit, is it possible? Is it allowed? To ask that question, then yes, it is possible only for 0 and 1. That is 0 can go to 1, 1 can go to 0. But what about the state like psi and arbitrary state? Can I take two psi orthogonal? Okay. If psi is alpha 0 plus beta 1, this orthogonal will be something like this. But you will realize that if you are familiar with your MSc level course, and if you recall your time reversal symmetry operation, you know that time reversal operation is not a unitary operation but an anti-unitary operation. Okay. And there, what you realize is if you want, if you have a simple two-level system like a qubit, to do a time reversal, you have to apply this kind of operation. Okay. Where C is conjugation and this is your Pauli matrix sigma y. Okay. And the C acting on psi is essentially giving you this conjugation alpha star 0 plus beta star 1. And this kind of operation, because this is anti-unitary, this can never be implemented physically. Okay. So that is the reason you can never be able to design a NOT gate for this arbitrary state or unknown quantum state. So coming to this partial erasure, what you want to do is you have a qubit which is like this, And if you are a high dimensional system, you can call it QDIT, and you can parameterize by 2D minus 1 real numbers like this. So if you recall what I said about erasure, you lose in all the information because given this input state psi, you want to reset to some state 0. Okay. So whatever information you have about the input state theta phi, you lose everything. Okay. But in partial erasure, you want to keep some information and erase only part of that. Okay. That is, given a state like this psi theta phi, okay, like this, you want to change to a state which depends only on theta. That means you are erasing the information about phi. Or you can keep about theta and erase about phi. Okay. Is it allowed? Then you will realize that again, using this kind of linearity of quantum theory, you will be able to show that this is not allowed. Okay. So what you learn from this is that complete erasure is possible, but partial erasure is not possible. Okay. So it may be true that quantum information, whatever that entity is, you can move it completely, but not part of it. Okay, so it is some kind of individual entity. Okay, so quantum information is some kind of individual entity. Okay, that is the implication of this. So then next, let me come to this loss of information. Okay, this is a very generic situation. This has been studied over several years, starting from 1991, under this so-called this decoherence program started by Jurek. So essentially, you have some physical system, and when the system evolves in time, it tries to interact with the external world, and slowly it loses its purity, loses its property, and so on. Okay, so once it does that, information slowly, degrades to the environment or ancilla or universe and so on. So in open system dynamical language, if you are familiar, we represent this by something like this. So don't worry about this mathematical equation here, but essentially your pure state, which is like this, transforms to a state rho, which is a mixed state. Okay. And in some extreme scenario, if your decoherence is so strong that it leads to complete loss of information, then what will happen is this rho will be independent of the input psi. Okay. If that happens, then you say this process is complete loss of information or information bleaching. So whatever was there inside, inside the input state psi, at the end, everything is gone. Okay, it completely washes out. So are there any physical scenario where actually this happens? The answer is yes. You have any scenario that does this kind of bleaching. So one example is state randomizing channel, quantum teleportation, quantum thermalization, black hole evaporation, and many more things. Okay. So in this scenario, you will see that the final state rho becomes completely independent of the input. So if that happens, then you can ask the question, where is the missing information? Okay. So whatever information was there in the state psi, that has disappeared, but where it has gone? Okay. So that is a valid question you can ask. And the no-hiding theorem is trying to essentially answer that question. Okay. Where is the missing information? Okay. So before proving the no-hiding theorem, let me tell you about this. How do you hide classical information? How much time I have? Okay, so should we find so? So classical information. I don't know if you are familiar, how to hide classical information, but essentially you can hide only in two ways. Okay. A crude example is the following: that suppose I have some file in my laptop. Okay, so how do I hide that? Either I can encode the information and keep a password so that nobody can have access to that, or I can take my laptop and take to home or go to bank and keep it in a locker. Okay, so only I can encode it or I can move it from here to there. Okay, only there are two ways to keep your information in a hiding manner. But the no hiding theorem will tell you that these two options that you have in classical world is not allowed. Only one option, that if you want to hide information here, you have to move it and keep it in some other part of the universe. Okay, there is no way to encode and then keep it secret. So one classical example is the following, that is something to do with one-time paired, also known as Burnham cipher. So there are two people, Alice and Bob. So Alice has a message, and she encodes the message M using some random n-bit key using this addition modulo 2. So this is the message, this is the key, and this is the encrypted message. And then she sent the message C to Bob, and Bob can retrieve the message by using again the key, which is essentially addition modulo 2. Okay. So if you look at the simple example and ask the question, where is the information? That is encoded bit string here has no information about them, and key also has no information about the input original message. So if you ask the question, where does the information reside? Neither in the encoded message nor in the key, but in the correlation between the two strings. Okay, this was proved by Shannon in 1949. But what we're going to show now is that no hiding theorem is going to rule out this option. Okay. So as I said, you can hide classical information only two ways: that you create correlation between pair of system, or you move it to some other location. Can you hide in the same way? So if you can do it, that is kind of quantum analog of this encoding. So you encode your message in the correlation with the condition that subsystem have no information. But this is not possible, and the theorem will tell you that if the original is missing, then it must be moving to some other part of the world, and you cannot hide in the correlation. Okay, this is the essentially message that is coming out. So pictorially, you can imagine like this: you have the input state psi, and this is the rest of the universe. And something happens to this psi, and you get a state rho, and rho has no dependence on the state psi. Okay, then the no-hiding theorem will prove that if it is missing from here, it must be found in some corner of the universe. Okay, it could be here, could be here, could be here, but it is there in some part of the world. Okay. But I think I will skip this the precise theorem. So let me tell you this. How do we prove this in an intuitive way? So essentially, what you do is you realize that any physical process is a unitary process in the larger Hilbert space. Then again, using the linearity and utility that I started with, you can prove that the information which is missing from the original is residing in the rest of the universe and not entangled with the pair of the subsystem. So as I told few seconds before, that quantum information which is missing from the original can be hidden only in one way, that is moving to the rest of the universe. Those who are familiar with quantum information, little bit, let me tell you one simple example. Okay, there is a channel called randomizing channel. So what it does is it takes input state psi and it transforms to a completely mixed state like I by D. Okay, so what it means is whatever was there at the input state psi, it completely bleach out. Nothing is there here. Okay, so if you take a qubit like alpha 0 beta 1 and you apply the Pauli channel like with probability 1/4 1/4 with all these elements, then you will see that the state becomes I by 2. Okay, so you can ask the question, where is the information has gone? It is not here, but where it is. Okay, then the no-hiding theorem will tell you that yes, it is not here, but it has gone to the rest of the world. Okay, I will tell you the precise statement or precise location where you can find it. So look at this unitary version. Okay, I said that any dynamics you can imagine like unitary process in the larger Hilbert space. So you imagine that your whole universe is essentially the input qubit and 2 additional qubit. Okay, you have 3 qubit system. Okay, and then you apply this conditional unitary operator like this sigma mu and mu, and these are orthonormal basis of this 2 qubit system like 0 0 0 1 1 0 and 1 1. And if you do that and apply on this input set psi and a, with A as equal superposition of all the orthogonal states of the 2 qubit, then you will see that the state looks like this. If you trace out this, okay, this part, the state of the final qubit is essentially I by 2. Okay, so this example is a very simple example to demonstrate how you can realize this dynamics in a unitary version. Okay, and the no-hiding theorem will tell you that it is not here, then where it is? It is actually, you will find that it is either in 2 or 3. Okay, so is that so? The answer is yes, it is indeed true. So you can show that the claim is actually true, that by doing only unitary operation on the Ancel-Hilbert space, we can find the missing information. So I have the final state which looks like this. Okay, if I look at only this part, I have nothing there. Okay, I have just I by 2. But the original information about psi, which is alpha 0 plus beta 1, that has gone to some part of this universe. My universe is only 2 qubit now, 2 and 3. Okay, so you will realize that by doing this control knot and Hadamard and this control knot acting only on this 2 and 3 qubit, you can recover the state psi. Psi is simply sitting in 3rd qubit. Okay, so this is the magical application of no-hiding theorem, that indeed the missing information which is gone completely from the 1st qubit, actually you can find in the 3rd qubit. And the no-hiding theorem is so universally true. You can apply in thermalization, you can apply in black hole evaporation, you can apply in many scenarios. Wherever you find the information missing, you can apply and find the information. Okay. And not only we proved this theoretically, but also we did the experimental test. Let me not spend time here. So I will show the figure that this was done in collaboration with Anil Kumar and one of his students in IIIT Bangalore in 2008, but the paper came in 2011. So initially we have a qubit like this, which is a coherent oscillation of 0 and 1, and this is additional 2 qubit. And then we do this unitary version. Okay, the control unitary apply. At the end, this becomes I by 2, but the state input, which is something like this, actually appeared here in 3rd qubit. Okay, this is the first experimental test of the no-hiding theorem using NMR setup. So finally, let me try to tell you about the no masking theorem. So essentially, the goal here is the following. Okay, so traditionally, we think that we can store information only in physical system. That is, I have a qubit here, I have one qubit, another qubit here, and I want to encode information either here or here. Okay, or I can also encode information in both qubit. If I can entangle these 2 pair, I can encode information in pair of this. But is it possible that we encode information not here, but somehow in this spooky correlation that exists between these 2? Okay, that means I have this 2 qubit which are in entangled state, and I encode the information not here, only in this invisible link. Okay, that means if I look at this qubit, I will not be able to tell anything. If I look at this qubit, I will not be able to tell anything. Okay, what I have done. But if I look at jointly, I will be able to tell what information I have encoded. Okay, is it possible? The answer is no, it's not possible. Okay, classically you can do it, but quantum mechanically you can never be able to do that. So that is essentially the motivation here. So we want to encode quantum information in bipartite correlation, and the condition that it is hidden from both the subsystem. Okay, since it is not here, it is as if we have put a mask here and we put a mask here. So that is why you call no masking theorem. Okay, so the no masking we coined because of this. So it is not here. If you look at this qubit, you will not be able to see anything. If you look at this qubit, you will not be able to see anything. Okay, they are kind of, we are putting mask here. Okay, can you do that? The answer is no, you cannot do that. So that is essentially no masking theorem. Okay, so if you can do that, then that will allow you to spread your information in smoky correlation and remain invisible to both the parties. Okay, both the subsystems. And the spreading of quantum information over quantum correlation we call masking. And then at the end, we will prove that this is not allowed. Okay. So what is the statement? Statement is actually very simple. So you have a operation, you have some input state, and you map it to joint state like H8 and HB, and these are the encoded states psi k, which are entangled state, with the condition that if you trace out either A or B, you will not be able to tell what is the value of k. Okay. This is exactly what I just tried to explain now. And you will be able to prove that given any arbitrary state, you can never be able to do that. So how do you prove that? Proof is a bit involved here, unlike no cloning and no deleting other things, but again, at the end, you can prove nicely. So what you do is you say that, okay, you have input state S0 and S1, and you encode into larger state like psi0, psi1. Then you assume that if you look at the individual part of psi0 and psi1, you will not be able to say what is S0 and S1. Okay, you assume that, and then you say, okay, let me do with the superposition state like mu S0 plus mu S1 and satisfy the same condition, and that will lead to contradiction. Okay, so that is essentially the intuitive idea behind this no-masking theorem, and it has several applications. So one of the important application is that you cannot have a quantum qubit commitment, and there was a very famous result in quantum information called no bit commitment. That follows from our result, and this kind of result also helps you to design what kind of state you can use to do secret sharing, and a lot of groups are working on this no masking, observable, and other things also. So it is beautiful applications. Okay, so quantum information is quite a vigorous field, quite developed field, but still there are many things still you're trying to understand, trying to get deep insights about that. So here is the reflection of what I tried to tell, that quantum information truly is an elephant. We are trying to understand by trying to investigate few things here and there, and so still many things are still yet to be understood. Okay, let me try to summarize what I said. So I try to tell you how different is quantum information from classical information, and by doing that, you will be able to tell what is really quantum about quantum information. Okay, and I try to tell you that classical information you can make copy, you can delete, you can flip, but quantum information you can never be able to do that. And no deletion and no cloning, they are connected to conservation of quantum information. And also I try to tell you that classical information is a physical but has no permanence, but quantum information is physical and it has permanence. Permanence in the sense that you can never be able to create nor be able to destroy it. Okay, if you want to create it, you have to bring it from some part of the world and keep it here. If you want to destroy it, you can never be able to do that. You can only take it and keep it in some other part of the world. Okay, so in that sense, quantum information is God. So I mean, don't take seriously, but yeah, in that sense. Okay, so I also try to tell you about why it is not possible to design NOT gate, and also it is not possible to partially erase, and that tells you that quantum information is some kind of individual entity. Okay, you can take it completely and put it some part of the world, but if you want to take it part of that is not allowed. Okay, and I try to also tell you that if information missing from some part of the system, you cannot hide in the correlation, and you can only take it and move it to some part of the world. And unlike classical information, I try to also prove that quantum information can never be able to mask it. And all these impossible operations are fundamental consequences of these two things, linearity and unitarity. Okay, I just started with this. Everything actually follows from this. Okay, so if you ask the question, what is quantum information? So to me, it is inexpressible in classical terms and is unclonable, undeletable, unflippable, indivisible, unhideable, and unmaskable. Okay, so if you discover something new, you can add here to this list, but at this moment, this is my definition. Okay, so that I thank you. So if you have any question.
Maybe.
Yeah.
I'm sure there are a number of questions. Dr. Arun may have some questions, but I would like him to conduct the question answer session.
But was it clear what I tried to convey? I mean, forget about mathematical definition or statement or theorems, but essentially the motivation and intuition. Was it clear? Okay.
It was a very enlightening talk.
Mhm.
We actually saw that we cannot handle quantum information. We cannot exactly handle quantum information and qubits like we normally handle and process normal classical data.
Mhm.
So my question is that, what is the scope of usage of quantum information? Like, can we actually use it in our daily lives?
Yeah, of course, using. I mean, in
Because
quantum,
we cannot.
in quantum computing, you are using quantum information. Your teleportation, you are using quantum information. You are using in quantum cryptography. Many things you are using, right?
But
These are the things that will tell you, you know, I mean, what you should do, what you should not do. Okay, you may think that everything I can do, but no, not that. Okay, so you should know. It's like setting the rules. You know, I mean, before driving on the road, you should know that you should drive on the left, not on the right, and so on. You know, so it's like setting the rules of the game. You know, so when you build a device in the future, you should know what is allowed and what is not allowed. Okay.
So the scope of usage of quantum information is very distinct from classical information.
Yes, yes, of course.
Like we cannot use them in the same place. We cannot use quantum information in
In
place
same,
of.
yeah, in same manner, same fashion, like classical information, you cannot use it, but you can use it, and you can use it in a more miraculous way, more amazing way. You know, so that is possible.
Okay.
Yeah.
Thanks.
Sir, you told that quantum information cannot be created or destroyed. So what about the information about the events which are going to happen in future? Can we extract that information?
Future information can never be, don't have control. No, you hold control only on present, right? I mean, future, how will you control?
So what happens to the information now that are going to happen in future?
What you can do or act on the system is the information that you have a time, a present time, time t equal to, okay. So in future, nobody can, I mean, nobody can predict about what will happen, right? So that is beyond the scope of quantum mechanics, right? So,
yeah.
Hello.
Just a minute. Okay, so can we finish? Okay, so yeah, please go ahead.
Sir, this is Panindra. I just have a question. So the quantum information can be calibrated or something?
sorry, I could not.
Yeah, we could
Hello?
not.
Can you hear me now?
No, everything is fine, but the last word, can you repeat the question?
Oh yeah. Is like quantum information can be calibrated?
Calibrated.
Putting in the standard scale or something?
Yeah.
Find the patterns.
This qubit is the basic unit of quantum information. Okay, so you can measure everything in terms of qubit. Okay.
Is it feasible, sir?
Yes, I mean, how many qubit you are using? Okay, how many entanglement bit you are using? So qubit and e bit are the standard of quantum information. Okay, that you can say.
How about calculating errors?
So, for example, if you want to do quantum teleportation, okay, like sending a quantum bit or quantum state from one location to another location. So you can say how much or what is the cost of doing this task, you know. So then you can show that if you use one entangled pair, which is one unit of entanglement, that is kind of cost of the teleportation. So entangled bit and quantum bit, they are a unit of quantum information. You can say that.
Sir, like considering one pair of qubit is fine, sir. What about like we have n number of pairs, like because we have infinite number of states, right, sir?
N number of pair, you say it is n e bit. If you have n number of qubit, you say it is n qubit system. Okay. So,
okay, sir.
Yeah, thank you, and we will.
Thank you, sir.
Sorry, I think I missed the point. So the place where you are talking about the time reversal symmetry. So what is the claim? So if I start from initial state, is it possible using some unitary transformation to go to some orthogonal state? Or
no. The question was classically. Sorry. Classically, I am able to design a NOT gate. Okay. So classical bit 0 or 1. If I've given that, I can always flip it to 0 can flip to 1, 1 can flip to 0. Okay. So also, if you're given a quantum bit in orthogonal state like 0 and 1, if you're given in this spin of particle, I can apply sigma x and flip it to 0 can go to 1, 1 can go to 0. But what about a state which is arbitrary state like psi, alpha 0 plus beta 1? Okay. Is it possible for me that I can change psi to psi orthogonal? Okay. So if I want to do that, then as I showed that the operation which will do this task is actually c times minus I sigma y. Okay, this is exactly the time reversal operation that you do on a spinor particle, single spinor particle. Okay, so because this is anti-unitary operation, that is why I make connection to time reversal operation. Time reversal operation is anti-unitary operation. Okay, that cannot be implemented physically, right? Okay.
So if I start with a general state, which is a superposition of, then I
you cannot
cannot.
do.
Then I can.
Yes, yes,
Okay,
yes.
thanks.
Yeah, thank you. Thanks, Arun, for a fantastic talk. I have one question. So some of these, for example, no deletion and
Yeah.
I think no mask. I don't know about masking, maybe hiding and not also this no orthogonal thing can be proved from one method, single method, all the theorems. Do we have anything like unified methods so that all the no-go theorems?
There are some approach. You know, some people have tried to do that, but I doubt that they can do everything. So for example, no cloning, no deleting, no flipping. I think these three theorems have been proved from a single kind of thing, but I don't know whether one can do everything. Not very clear. Yes. Yeah.
Thank you. So yeah.
Thanks, Professor Pati. Two questions. So in your all this no hiding theorem, you are talking about a system environment setup. So and what you have shown that it looks like they are written in a product state form. So is it always required that the system environment is like a product?
Initially, the time to equal to 0. Yeah, initially you start with product state, and then evolve by joint unitary, and then if you trace out the one part of the system, then you will see that the system obeys open system dynamics. Okay, that is what in quantum information we say, Krauss formalism or open system dynamics and so on. Okay, or Lindblad approach, whatever you want to call it. So initially, this and this there are product state, then you apply unity operation, then evolve it, then trace out one side. What you are left is essentially your open system dynamics. Okay.
So I was wondering if I am given a scenario where you, for example, the ancilla and the qubit or the system environment, they cannot be written in a product form. And then I have the mask theorem.
So if you don't have a product form, then it's not possible to there are other directions. There is a lot of research going on about how to define a Krauss operator formalism and open system dynamics for initially correlated state. Okay, so there are already some results which says that if the system and the ancilla they are in correlated state, then the reduced dynamics may not be completely positive. So I want to technically go into detail that kind of thing. Then what will happen is if there is some kind of correlation initially between system and ancilla, and you evolve it and trace it, it might turn out that the density matrix of the system may admit some negative eigenvalue, which is not allowed, right? We know that state to be physical state, it had to admit positive eigenvalues, right? So there are some problems, but there are a lot of things. I mean, people are investigating that kind of scenario. So. Yeah.
So one more question is that what sort of no-go theorem one can talk about when there is a measurement involved? Like everything you said is no measurement scenario, right? All unitary.
Yeah.
All maps are unitary. So what if there is some measurement involved in partial?
No, if you bring complete measurement, okay, that is also kind of Krauss operator formalism. We can write in our open system dynamical formalism. So everything will go through. But if you do a selective measurement, then there are some things wanted to worry about. But if you think of a complete measurement process, then this falls in that category also. Okay.
Okay. Thanks.
Thank you. So I think.
Just check if there is a question.
Yeah.
First of all, thank you, sir, for the wonderful talk. And I want to ask, like, you talk about this no hiding theorem, where this information is somewhere else in the atmosphere, in the environment. So I want to ask, like, if it is interacting with the environment and someone in the future wants to extract that information, so could he able to extract the complete information because it will not be the same information.
No.
Because with the time it is interacting with the environment.
So the answer to this question is in principle, yes, but in practice, it may be too complicated, too complex. You know, you don't know what kind of operation you need to apply there and recover the information. But the answer is in principle, yes. As I showed in that simple example, up to that local unit like C node and Hyderabad and C node, the information is still there, right? So in principle, it is there, okay. But whether I can recover it, with what effort I can do it, that we don't know. I mean, that is not answered by no-hiding theorem. No-hiding theorem only tells that if it is missing from here, it is there in some part of some corner of the node. Okay. So that is the statement. I mean,
okay, thanks.
Yeah.
Thank you, sir, for the nice talks. I have a rather general question. So it's usually possible to derive classical mechanics as a special under limiting case of quantum mechanics. But here it seems that classical information and quantum information are treated very separately. So is it possible to derive classical information or define it as under certain limiting case?
Of course. I mean, as you see, the no planning theorem, the first theorem, no-go theorem, is only for a completely arbitrary unknown state. But if you're dealing with orthogonal state, you can do it. And to connect to classical world, essentially, if you store information in orthogonal state like 0 and 1, they are the classical information. Okay, and I can do it. I can copy it. I can delete. I can mask it. I can do everything. So whatever I said actually follows a special limiting case. Okay. So,
the last question. Somebody posted in the live chat in YouTube. He's Mr. R.K. Pradhan, and he is asking, can we say, quote, all information is fundamentally quantum?
Yes, in principle, yes. Because everything, if you believe that whole universe is ultimately quantum mechanical, then yes, all information is quantum. But you see classical information. So classical information is kind of a decohered version of, classical information is dephased, decohered version of quantum information. Okay, at the basic level, everything is quantum. Okay, that you can say yes.
Thank you.
Yeah.
Thank you, sir.
Yeah. I have one follow-up question. This is regarding this, I forget the name of the author, but Selby is one of the authors. And he had another no-go theorem that there will be no theory to which quantum mechanics would decohere. So is there, this is another no-go theorem of sorts.
I've not seen this. Is it a recent paper or?
Yeah.
If the quantum theory decoherence, if the theory doesn't have the entanglement, then it cannot decoher to class. I think everyone.
Yeah, I've not seen this.
Yeah.
Maybe I
But again, there were some conditions and so on, so I don't know what the status is. But
that,
anyhow, means.
Quantum has to have an entanglement.
Of course, that is, I'm intuitively clear. I mean, unless you interact with the external world, how will you get classical? So classical it will emerge only when you interact. Once you interact, you will get entangled. So if you stop entanglement, you don't allow entanglement, of course. I mean, to me, it looks obvious, but I don't know how to see that paper. I don't know.
So anyhow, thank you very much. So I think for want of time, if you have any further questions, you can send an email. So thank you very much, Professor Pati.
Thank you.
And you know, there are large number of persons who we should thank for the wonderful talk that we have been able to have today and the series of talks. So I'm going to request Sunil to propose a vote of thanks. But before I do that, let me thank Sunil because CAMOST is what it is because there are a lot of people who contribute to it. Sunil is a program coordinator for CAMOST on behalf of IISER, and Arijit Sharma is the program coordinator. So they do the basic operations for the center. And there are other colleagues. I mean, Sambudha is here, so he also contributes a lot. Vinay is here, Arvinda is here. So there are a large number of persons. But let me request Sunil to propose a formal vote of thanks. Thank you, Sunil.
Hello. Yeah. Okay, thank you. Okay, good afternoon. So I would like to convey my sincere gratitude towards everyone who has made this event possible. So first of all, I would like to start with Professor Arun Kumar Pati, who kindly agreed to our invite and came here for this exciting presentation without going into the technical details. So it was easier to follow for those who are not really experts in quantum technology related research. Okay, then okay, the next based on the whole thing could be conducted only because of the CAMOST, and I think the first person to whom I have to thank is Professor P.C. Deshmukh. So because he is behind this center itself. So that is first thing. And then we had a lot of guidance and no, yeah. So then there is Professor K.N. Ganesh and Professor K.N. Satyanarayana. These are the directors of IISER Tirupati and IIT Tirupati. So they have been at the forefront to support us and guide us to create this center and make everything possible. So I would like to thank their contribution in supporting the inception of CAMOST and nurturing it throughout the years. So then I would like to thank Professor Shantanu Bhattacharya, who is the new director of IISER Tirupati. So who has been very supportive from the beginning, just after joining. So this is the first meeting we have after he joined, and he was very generously supporting us to conduct this program, including the financial support. And then there's the Dr. Aditya Banerjee and Dr. Chitra Sanjana and Dr. Ritesh Gangwar. So these are actually constitute the administrative council of a CAMOST. They were very supportive in helping us to get the place and resources ready for this. And even Chitrasan is here. Thank you, Chitrasan, for joining us here. And then, of course, there are so many CAMOST members who are like a faculty from IISER Tirupati and IIT Tirupati who have been supporting us throughout this program. And this is just the beginning. And there are so many other talks which are going to come back. Come and for that, I need really support from them. Many of them have agreed to conduct the sessions, and I would like to thank every one of them. So then, of course, the administrative staff from IISER Tirupati and IIT Tirupati, mostly then the IT people, and then the other people who are actually set up all these things which you see here, and I would like to thank them. And then we have so you can see that IAPT, the Indian Association of Physics Teachers, is our outreach partner. And so I would like to convey my gratitude towards their support. And Professor Ahluwalia, who is the president of this IAPT, I would like to thank for his guidance and support. And then Professor Ashutosh Sharma, the president of INSA, and Professor Narendra Mehra, who is the vice president of INSA. I would like to thank their support because they are also like co-organizers of this conference. Even though they are not physically present there, they have supported us a lot to get it started. So then finally, I would like to thank all the students and all the faculty members and also the online for participants who have joined here to make it as an eventful event. And thank you all. Timings are going to flawed because people are
Yeah. Can I end this screen?